Oh, so chapter 38?
Yes, I think so.
Well, that's it, it said modern physics in the atom.
Yeah. However, before we get there, let's talk about resolution.
Oh, right there.
So, we talked about the single slit. You've done an experiment with not only a single slit, but sort of the reverted single slit, in other words, the hair. And you got the pattern where you have the bright spot here, and then it lessens. If instead of having just a slit there, where you've got the two dark bands, and then you've got that one little opening right there, suppose it were just a hole. So if you're shining light through a hole, then you also, in essence, you have single slit diffraction, except the pattern that shows up is not going to be, you know, the bright spot and then it's sort of strung out like that, but it'll be circular because it's basically diffracting in every direction. And so you get a bright spot in the middle and then a dark band, and then you'll have another bright area and then another dark band. And badly drawn, but I hope you get the idea of the concentric.
Sort of like I was just saying, sort of like the waves on water when you throw something into the water. Kind of like that?
Yeah, it would be like that.
Yeah, hopefully it didn't interrupt something.
No, it's fine. If we looked at a cross section right here, the pattern would look a whole lot like that. Now, the size of this middle spot here depends upon, I think, hopefully somewhat obvious, depends upon how far away the laser is, or more specifically, how far the hole is away from it. But the radius of this bright spot in the middle, which has a special name, which I'm blanking on at the moment. Stuck it over here. The Airy Disc. The radius of this Airy Disc, there's a particular formula for it that I would love to be able to derive for you, but I can't. Theta equals. In other words, if I've got my hole here, and then the Airy Disc is basically taking up that area, we're talking that angle there.
Is that 1.220 or is that?
1.220,
Okay,
yes.
Okay.
And over the diameter of the Airy disc? Is that what?
All sorts of little mistakes today. It's going to be one of those days. This D right here is the diameter of the aperture.
Oh, okay. Okay.
I think that's spelled right. And that's obviously wavelength of light. And theta is the angle that basically where the Airy disc is being broadcast. Now, the derivation of that, there are a whole lot of sources that I was trying to find. I was trying to go through the derivation, and there were a lot of sources that basically started with the answer to what I wanted. So just to explain some of the, why didn't they do better than that? It should be back here somewhere. The intensity of the Airy disc as a function of theta is some base intensity times 2 times the decimal function of order 1 think I got a mistake there because something's off. This is the bad boy right there. So during, I think it was primarily the 19th century, there were a lot of mathematicians who basically what they did in order to get status was they were given, hey, here's a problem, solve it. And so they didn't always come up with a solution. What they did was, well, if you have a bunch of letters in it, they say, well, if this letter is equal to 2, here's the solution for it. If it's equal to 3, here's the different solution for it. And so, in essence, they come up with these ordered functions, and Bessel was one of the guys who was creating it. There is something wrong with the equation, so I'm going to sort of stop right there. But coming up with that, I started looking at the derivation of that one, finally found it, Wikipedia. None of the physics sites, but Wikipedia did it. And I thought, that's going to take a whole lot of days to figure that one out, so I just basically stopped and went back to, let's trust that they knew what they were doing.
Okay, so no need to be concerned with the derivation.
No.
That's good.
But there is something wrong with the equation that I've written down there, so I haven't quite figured out what. I'm gonna have to go back and look it up for my own edification. All right, so if I've got so I have this, basically this image right here, and you can sort of think of it as in reverse as well. If I have a disc that's coming into, say, a small aperture like your pupil, we would see this. But if I have two objects, both with a spot right there and right there, I'm assuming everyone in here can see this as two distinct spots. But if you go back far enough, at some point, you won't be able to tell, because our eyes have a certain resolution. If I looked outside, I'm not sure I could pick out two different blades of grass right next to each other. From experience, I know there are blades of grass out there, but being able to separate two of them becomes very difficult. And so, what I want to go through is, I guess, Thomas and Kong, either of you wear contacts? Just both have good vision?
Terrible.
Good vision.
Yeah, I'm purposefully not talking to Aaron and Holden and myself at this point.
So would you say resolution's sort of like your eyesight? Because let's say like Con or him, he can kind of see the borderline between, say, those markers. Whereas me, is they kind of look like they fade in together.
And you see the rainbow.
Yeah, pretty much, yeah.
I can see two of everything unless I really try to focus.
Well, you're also closer too. And we probably have different vision.
And generally, when you're talking about eyesight, you could connect it to this, and if your glasses are working properly, if they're putting the focus on the right part of on the eyeball in the back,
yeah,
then you should be able to do this as well. I know from my experience it gets a little bit off when I try to do this next bit, so that's why I was lumping you into the same category as I am.
I gotcha.
Would resolution be how easily the quality of an image? Would that be a good way to describe it? Or is that sort of too vague?
I think probably closer to it is resolution deals with the ability to distinguish between different objects.
Oh,
So
okay.
when Aaron was talking about, I assume with your glasses off, it's just one giant blur, that's horrible resolution. I mean, here I can see definitely a distinction between this marker and that marker, but if I'm back where Aaron is, I don't know if I could. I'm just sort of curious at this point. Without glasses. Well, I know what the marker looks like. If I walked in here without knowing what a marker looks like, I doubt if I could point to the beginning and end of it.
Yeah, I can't, I'm having a hard time reading the stuff. I have a hard time reading the brand and stuff on it.
Yeah, I'm gonna say that, your vision's better than mine because reading
I can't read
is
the
not
board.
even close.
I can't read the board either.
I think, maybe that's just,
Yeah, and the two dots actually look like a dot in the middle and then with parentheses around it right now. All right, so what I'm curious about is the resolution of dots. And so I have an eye chart here. Now, I am assuming that I will use Kong and Thomas, that you can see two distinct points here.
Yes.
All right, let's go into the hallway, we got more room.
You want me to turn off the recording?
Or pause. Let's make sure I put the two in the right spot. All right. So basically, the criteria,
I started it again.
you did, okay, thank you. The criteria for resolution was when the two dots basically blur together. So that when the distance between the dots is basically the radius of the dot. So the overlap where it now looks sort of oblong. So we were 7 meters away. Sorry, I projected there, 9 meters away. You were 9 meters away. The distance between the dots in reality was 0.48 centimeters away, or 0.0048 meters. And so the angle in radians is basically that ratio right there, 0.0048 over 9. If someone would be kind enough.
Oh, sure, I'll take care of that. We're into number 9, 5.33 repeating times 10 to negative 4.
That's radians. Which is how many degrees?
What was it, pi divided by 180?
No.
Be times 180 divided by pi.
Oh, sorry. 0.0306. I'm just rounding up.
Yeah.
We go from grades to
Same thing?
grades, it's times 180.
Yes,
divided by
the
five.
same thing.
Okay.
Wait, did I do it right?
0.305?
Yeah.
0.0305?
Well, 0.30, 0.36.
Yeah, we rounded.
Yeah, because
Alright.
I rounded.
Actually, I want to keep it in radians here. So my angle, 5.33 times 10 to the negative 4 radians is equal to 1.220 times the wavelength. And I deliberately made it blue, which was, from what we did yesterday, that blue light, different shade obviously, but ballpark.
It was 410, something like that.
410?
Or
Oh, I
405.
think we actually counted. Or either
Hold
one.
on. Blue,
What's the manufacturer say?
405.
405.
405.
405, yeah.
yeah.
Times 10 to the negative 9 meters, divided by D. That's the size of the aperture, that's basically the size of your pupil. What are the chances this is actually gonna come out to something even close?
And and if I recall, the pupil will change depending on,
The amount of light.
yeah, so.
I got a range here, somewhere in my notes. Thank you. What color it up? Oh. There we go, finally found it. All right, so what do we get for D?
Already I got 9.27 times 10 negative 12
Units?
meter.
So we're talking about point, see, we've been over 4 spaces, so 0.9 millimeters. And officially, the pupil are supposed to be 2 to 9 millimeters, depending upon various lighting situations. So we're only off by a factor of, more than 2. One of these days, I'll get a group that sees things the way they're supposed to see it. I'm trying to think that, because the factor of 2, we're not off by that, we're not off by a factor of 2 here, so that's not bad. Yeah, oh well. And that's basically what I wanted to say about resolution. And now to the fun stuff. Any questions? Oh, we officially finished chapter 37, I believe. Today is the 7th?
Yes.
Week from today. Quiz on chapter 37.
Do we have to worry about polarization? Hopefully hopefully it didn't cause any problems, because that's.
Oh. I don't have a polarization tab.
Yeah, it says,
What is polarization?
Well, let's talk about polarization. It's not gonna take long.
yeah, sorry guys, I just noticed it in it, I have the book out and I saw it was in that chapter, and
Yeah, it's in the chapter 37.
and I didn't know if it would be on the quiz.
It's like only allowing light through
That is not
a screen that's like in a certain orientation, something like that.
I know that some sensors use polarization.
I'm gonna go grab the overhead projector, because it works better with that.
I got to commission 2 panels today.
What?
I thought you didn't have to work on Mondays.
What?
I thought you didn't have to work. Oh no, it's Wednesday, isn't it?
Yeah, and that's kind of changed. I wish I didn't, but with as many responsibilities I have at that job, I can't take. It's gonna be long. Well, I'm not good enough. I'll get backed up, basically.
I'm just sending my RSVP.
You did?
I know I need to.
Yeah. There's the head count, so you know how much food you get.
Yep. I remember when my sister got married.
Oh, I see.
There's like, a bunch of people who were just like, they were just like saying, oh yeah, we're coming.
Yeah.
And now I filled out RSVP.
Well, I just realized, we probably don't have anything on polarization, there's no, math equation associated with polarization.
It's already pre-stamped, so I'll just go back from there.
Okay.
No, yeah, it was valuable time.
Bring somebody with you? No.
All right, so light is made up of electric and magnetic waves that are perpendicular to each other. The electromagnetic waves, I'll have an electric wave, let's say that's parallel to the board, and the magnetic wave would be perpendicular to the board, badly drawn as such. So I got a magnetic wave coming out this way, the electric wave coming that way. From a head-on point of view, if it's coming straight at you, an electric wave this way and magnetic wave that way, and it'll oscillate back and forth. The electric wave starts out one way and then flips. Same with the magnetic field. Or electric field, I think it's called the electric wave, electric field. So what polarization does is it comes in as it blocks out blocks out light that is perpendicular to these very thin, I guess, openings in here. Badly worded, but you get the gist of it. Now, light is not perfectly, electric field is not always this way. Electric field might be like that. So if that's my electric field like this and magnetic field this way, well, they would all tilt the same. So if I have an electric field line going like this way, magnetic field line is coming like that, and if I blocked anything, if I put the filter so only vertical stuff gets through, we'll recognize I'm not blocking this, I'm just blocking part of this. Because any vector, because it is a vector, can be broken into components. And what gets through, if I allow the vertical stuff to get through, would be this component of the electric field. So if I have light coming in all directions, then what in essence the polarization filter, one polarization filter will do is to block all the light, block half the light, all the light that is perpendicular to whatever is being allowed through. And let's bring this down. All right, so that's a polarization filter right there. And half the light, that should be half as bright as the other one. I have a second filter right here. And I actually want a third filter. So I'll let you sort of contemplate the Zen nature of what you're looking at.
I'm going to say that one on the right is half of that one on the left. So that one on the right is a quarter of what's.
Yeah, that's what I'm thinking too.
Huh?
Oh, they do look like they are different colors. We'll bring a third one in. All right, so these two look the same. This one does look. Let's see if I can find. I'll filter more of these.
Oh yeah, you can tell just by looking at them. They're different.
Those look closer.
Yeah, they do.
Where's that the one I just pulled out? All right, so one of those is not like the others.
Yeah, the one on the bottom left.
All right. Hopefully those are close enough. All right, so I put one on top of the other, and obviously it's darker. I got two polarized filters here, but now if I rotate one of them,
And it's dark.
I block all of the light. So basically the polarization of each of these filters is perpendicular, the polarizations are perpendicular to each other. So I'm blocking, one filter is blocking all light in one direction, the other one comes over top of it and blocks whatever's coming out. Now, the crazy part about this. So I have light coming in all directions, and let just this be my electric field. I put in the filter, so I only allow vertical to come through. So this is all that's going to come through, all the vertical stuff right there will come through. This, there'll be less much. There's some English for you. I'm only taking in the vertical components of the remaining stuff. So in essence, that's what's getting through if we consider this is just the component of all these other lines. I'll put the other filter over it, and since all of it's vertical, it all gets blocked. However, if I stick another filter that's at an angle here, so I'm now only letting through stuff that is parallel to that. Well, all of these lines have a component that is perpendicular. or sorry, the component that is parallel to this. So for example, this one right here, I've got a component that way and a component this way. I'm gonna block the part that's perpendicular to what's being allowed through, but some of the light will be let through. So now it's gonna be less, it should be darker than what I had before. It's dark, definitely darker than that. It's darker when I had one polarization filter on, but now I've got less light coming through. And then on top of that, I take my polarization filter and I only let perpendicular go through. Well, each of these has a component that is parallel to this. So there's a part that is in that direction and part that's in that direction. I'm only blocking that part. So what I'm talking about practically here I've blocked out all the light here from these, and if I rotate it 90 degrees, if it's perfectly lined up, and these are perfect filters, because that's the way life works, the overlap should be roughly the same brightness as each individual one. That's probably the best I'm going to get right there. So those are lined up. So anything that passes through one filter will pass through the other one. I rotate the top one here 90 degrees. Let's see, somewhere around there. Rotate it 90 degrees, and I block out all the light. That's what I did the first time. Now I'm going to take another filter, and I'm going to put that in between. Okay, it's all blocked out. I'm going to rotate the middle filter. And you can now see some light coming through. Now it's still incredibly dark there, so let's turn some lights off. I'm going to remove the middle one. Okay, they are lined up when it's the brightest, and then, all right. I think we can agree no light's getting through.
Yeah.
Take a middle filter, and suddenly light's getting through. So when this middle filter, this one right here, is at a 45-degree angle to the other two, that's when you're going to get the most light through in this middle filter, or through all three filters. I remove it, no light, I put it in, there's light. And then I can rotate the top one again, or darken it. And we now have a Venn diagram. Anyway, that's the essence of polarization. Questions?
It's awesome.
Pardon?
It's awesome.
Oh, yeah. I'm also really curious about what's actually going to show up on the video. How well it can be seen.
This concept's like polarized sunglasses.
Yeah. So the polarized sunglasses, I believe invented by a Harvard dropout. Like Microsoft and other things like that. The way polarized sunglasses were explained to me is that if you take polarized glasses, and in theory light's coming in all directions, there's no particular orientation, so it shouldn't really matter how you orient the polarized glasses, just so long as they're polarized. They'll let half the light in. However, if you look at reflection of light off of, say, water on a pool or something like that, that tends to have a specific orientation, and so it is. So I think, if I recall correctly, the electric field lines tend to be parallel to the water when it bounces off, and so if you set polarization this way, you should get block most of the reflective light coming from down below, and then half of all the light just coming straight in. So I think that's the way that they were polarized specifically for that.
Yeah, I've heard they were designed to get rid of the glare off of the reflective surface like water.
Okay. And then you've got another use of polarization is the 3D polarization.
Mhm.
That those lenses are oriented differently, so I think from what I recall when Epcot Center back in the mid-80s, that the polarizations are at an angle like that. So why that works and your brain processes it and get that 3D image, I'm not 100% sure, but.
And I heard that they use polarization in the security, like they transmit information through polarization. I don't understand about that, but I found that on internet.
So they use that for security.
Yes, like they send the light through the fiber the fiber optic.
Okay, fiber
Yes.
optics.
And they use polarization to send the information there. And the other side they will use the same polarization, but it should be match the polarization that the sender, so you can get the information from the light.
Okay,
If both sides have the same polarization, but if one of them doesn't know what the other operation do, we never get the information from the lights through the fiber
Yeah.
optic. But
Okay.
I don't understand about that, but they have a research about that.
I
So-
can see that.
basically you've got the fiber optic cable.
Yes.
So if you send and light generally comes in at any angle, but if you send in a coded message with a certain polarization to it,
Yes.
then at the other end, as long as you're looking for light with that polarization,
Yes.
you basically would filter out half of the background noise. Huh. My first thought was, man, the sophistication we would have to have, and I thought, oh, wait a second, we probably have that.
Yes. Yes.
Cool.
Yes. Cool.
Noise is a big problem out in factories.
Alright, we got anything else from 37?
Nope.
Okay. Any other questions or comments before we talk about why everything you've ever learned is just a little bit off?
There's a hard ceiling,
What's that?
so there's a hard ceiling on velocity.
Ah,